This is the first video about how to solve disjunctive scheduling problems using constraint programming. So I'll start by explaining what the Jobshop problem is, and I will start by explaining the decomposition of the disjunctive constraint. So the Jobshop problem is represented here. You have a bunch of jobs that needs to be scheduled, and each job is composed of a set of activities. In this example, there are 6 activities for each job, and the activities in each job must be executed one after the other. So there is a precedence constraint between each of them. That one must be executed before that one, and so forth. And as you can see, there is also a color code for each of the activities. And the color code represents the machine on which the activity must be executed. So if I take, for instance, the light blue activities here, all of them must be executed on the light blue resource, and they cannot overlap in time. And so you can see that it's the case here. So if I take any pair of light blue activities, they do not overlap in time. It means they execute one after the other. This is exactly what we mean by a resource with capacity 1. And so that's the case for every color code. And so the objective function of the Jobshop problem is to minimize the make span. What we mean by the make span is the latest execution of any activities. We want to push everything to the left as much as possible. And so this is the make span minimization that we want. That's a very difficult problem, and the decision variables that we need to fix is the starting time of all the activities of that problem. That's the Jobshop problem. And to model that problem, we need one specific constraint to encode the fact that all the activities executing on a specific machine cannot overlap in time. That's called the disjunctive resource, and we also sometimes name it the unary resource. It's a very specific case of the cumulative constraint that we have already seen, but in this specific case, we have a capacity of 1, and we also have that every activity has a resource consumption of 1. And so they cannot overlap in time. So do we really need a new constraint to model this disjunctive resource? Not exactly. Actually, we can model this global constraint with a set of pairwise activities. So we can state that for every pair of activity ij, either activity I executes before the activity j, so that's this case, for instance, I is executed before the activity j, or the opposite. So either j is executed before the activity I. Okay? And so this is captured by this less or equal relation. We take the starting time plus the duration. Actually, that's the ending time of the activity I. And so the ending time of the activity I is less than the starting time of activity j. Or that's the other way around. So the ending time of j is before the starting time of I. But we don't know which one of the two relations will hold, and therefore we use what we call a verified constraint. And so this Boolean variable, that's a 0-1 variable, will capture the fact that the relation is true or not. And so one of the two must be true. Either I is before j or j is before I. And so you do that for every pair of activity ij, and you end up with a model for the disjunctive constraint. So that's one possible way of decomposing the unary resource constraint. And if you remember about the all different constraint, it's pretty similar to the idea of the all different constraint. For the all different constraint, we had this idea of every pair of variable must take a different value, right? That's a little bit similar to that one, except that we use less or equal constraint instead of the not equal relations. But another natural definition comes from the definition of the unary resource itself. We could use the cumulative constraint to model the disjunctive constraint. We just need to specify that all the activities requires resource, 1 unit of resource, and the capacity, so that's the capacity of the global constraint is equal to 1. So that's another possible way to model the disjunctive resource. Which one is the best, of course? That's a very interesting question. And to answer that question, I will use a very small example. So let's consider first the decomposition using the timetable filtering for the cumulative constraint. So we use the timetable filtering that you already know. The timetable filtering, if you remember it first starts by building the optimistic profile using the mandatory part of the activities. If you consider that examples with activity A and B, there is no mandatory part at all. So it means that we will not be able to print any value from the domains of I or of A or B. But if you use the verified constraint and you say that A is before B or B is before A, you can clearly see that it's impossible to execute B before A, given here the interval that we have for the execution for A, right? If you put B completely to the left, let's say we put it there, for instance, there is no space for A, right? Because if you put A here, you see that there is an overlap. So that doesn't work. So we know for sure that we must have that A is before B. We know that. And since A must be before B, if we put A completely to the left, which is the conservative way to print the activity B, we know that we will remove these values from the domain of B. Okay, and so we will get some printing. So this example illustrates the fact that the binary decomposition is stronger than the timetable filtering to model the disjunctive constraint. Let's come back to the Jobshop problem and see how to model it with mini-CP. So we start by instantiating an instance by reading the file. So we read the file here, okay, which is specified here. So that should be the path to a valid instance file. Then we create a solver, and then we will introduce one matrix of start variables. And this matrix is this one. You see that there is here n jobs. Okay, that's the n jobs, and that's the n machines, right? So that's the matrix of activities. They are represented here on the right. And then we also have the ending time of all these activities, and the ending times is linked to the start time by doing end is equal to the start plus the duration, right? With the plus relation here. I forgot to mention that the upper bound on the domain of the starting time is what we call the horizon. It's something that is very large, right? So let's say that h is very large, so that it's not really a constraint to use it. So it can be, for instance, the sum of the duration of all the activities of your problem. Then, of course, we need to model the precedence constraints of all the activities. And so we will iterate over every job one at a time. And over every job, we will consider the activities, in that order. So we say that one is before that one is before that one, and so on. And we will model that with a less or equal constraint there. Then we have the disjunctive constraints. We will iterate over every machines. We call M, the machine index. And we will use a helper method that is available in the instance, in the Jobshop instance class, collect. And collect is able to collect all the variables related to a specific machine that is provided in argument, which is M. And so I will get here, for instance, all the blue activities. So, for instance, I will collect all the blue activities with collect. I collect the start time of all these ones, I collect the duration of all these ones, and I post my disjunctive constraint there, providing in argument the starting time and the duration of all the activities, executing on that specific machine M. Then I need to model my make span minimization, okay? And if you remember, the make span is the latest end of all the activities. And to do that, I will capture the last activities of each job. Okay, I collect the last activity of each job. I collect that in end last. And then I will use the maximum constraint that you have implemented as an exercise. And this maximum constraint will give me the make span. And this is exactly the variable that I want to minimize to push everything to the left as much as possible. And for the search, I will flatten the start times variables, and I will use the first fail, for instance, to fix the start time of all the variables. And that's it for the model of the Jobshop problem. And this concludes our introduction to disjunctive scheduling.